All right, so let's do that. Okay, Riley has, all right, so I think shall we start? What do you all think? Maybe let's start with with a little bit of an introduction, and then we'll see if anybody else joins us. It's going to be a small group. So, good morning, everybody from Mississippi. My name is Narcisa Pricope, and I am the organizer of this session, the proposer. I have been with the Global Land Program since its very first Open Science meeting back in 2010 in Tempe, Arizona. I was actually a PhD student at the time, and it was one of the it was one of the coolest conferences I had ever attended. So I've been a GLPer ever since. In GLP for about 7 years, I was a co-lead for the working group on sustainable land systems, co-production of sustainable land systems. I helped organize a variety of events and drive forward some of the initiatives on co-production at GLP. We were actually the first working group. Now there are quite a few more. So that's been my engagement with GLP. I'm a geographer by training, and I'm currently a professor at Mississippi State University. So I'll turn it over to my other two Mississippi State colleagues, Dr. Prakash Jha and Nafiz Rahman, to introduce themselves.
Good morning. Good morning, Dr. Prakopi. Good morning, everyone. My name is Prakash. I'm Assistant Professor of Agriculture Climatology at Mississippi State University in the Department of Plant and Soil Sciences. I do work in the intersection of remote sensing, modeling, and land system science, you can say, for agriculture area, where we talk more today. And thank you for having me on the panel.
Absolutely. Well, thank you for joining us. Nafiz?
Yeah, good morning, everyone. I'm Nafiz. I'm Dr. Narcissus' PhD student. I'm doing my PhD in Earth and Atmospheric Sciences at Mississippi State University. So I have research interest in remote sensing, geospatial science, geo AI, and similar fields. So looking forward to talk today and connect with you all.
Thank you so much. And last but not least, our colleague from Oak Ridge National Laboratory. And for those of you who don't know, Oak Ridge National Laboratory has about 120 geospatial scientists working in the Geospatial and Human Security Division. So Debrat Varshny, sorry, will be speaking to us today on some of their work at Oak Ridge.
Yeah, thanks. Hey, thanks, Narcissa, for having me. Hi, everyone. I'm Devrat Varshney. I'm a postdoc at Oak Ridge National Lab working at the GeoAI group. We mainly work on different diffusion models, generative AI for synthesizing remote sensing imagery, a bit of multimodal like foundation models for different downstream applications. And yeah, my background is in computer vision, machine learning, applied AI for geospatial data sets. And yeah, it looks like an exciting talk. So happy to be here.
Awesome. Well, thank you, everybody. I feel like people are still trickling in, so maybe one of you can keep an eye on the participant list and admit people as they come once they start sharing screen. Okay, thank you very much. So let's get started. I have a very brief little presentation to kind of to situate why I proposed this session for us to. Oh, I just saw somebody trying to come in. So you guys, can somebody admit? Can one of you? Okay, you got it. Okay, thank you very much. Wanted to start with that. And again, I've been engaged with the Global Land Program for a very long time from the get-go. I'm excited about this Week of Land System Science inaugural event. And I thought, my gosh, what could I propose that's a little bit different for us to think about as land system scientists? Again, I am a land system scientist, a geographer by training, came through University of Florida in a very interdisciplinary program. And over time, since I finished my PhD in 2011, so it's been a while, but over time, As I work in this space, I've found myself moving closer and closer to something that I like to now call environmental intelligence. So, how can we leverage all of the amazing work that we do as lens system scientists to operationalize and help speed up decision making? And again, that's kind of the broad umbrella of why I proposed this session. Actually, the context, again, a little bit more context on this environmental intelligence, which came from work that I've been doing for the last about 10 years in geospatial intelligence. So the idea that we can take geospatial data and geospatial streams of information and use it for anticipatory decision making. In the same way, all of the work we do under land system science pertains to environmental dynamics, human environment, coupled human natural systems dynamics. But oftentimes there's a bit of a lag or a bit of a gap between all of the incredible work that is done in that arena and how that work is being leveraged for anticipatory decision making. So as I said, that's where the idea came to me, and I'll contextualize a little bit, even a little bit more, on to why I decided to go this route and kind of open up this conversation and see what some of y'all in this field are thinking about how we can take this amazing advanced capabilities that we have to model, observe, and explain environmental changes, and essentially move that into anticipatory decision making, where we can start not only anticipating risks, but prioritizing our interventions and beginning to be able to give actionable intelligence to those who may need it. So that's sort of the shift in thinking here that I'm proposing from mostly and I'm not saying all of land system science is descriptive. That is not what I'm driving here, but oftentimes we spend a lot of our time in the explaining of the how and the why and what's occurred, and then working on publishing and doing all of that, and spending a little bit less of that our time into thinking about, of course, as academics, we would, into how we can turn that information into decision-making relevant outputs. So I think for us as land system scientists to move closer to a field of that becomes more decision relevant into an environmental intelligence, we really need to be thinking about three really critical capabilities that, and again, we have the ability to do so in land system science. How do we detect signals? How do we find early indicators in heterogeneous, noisy, multi-scale data that is oftentimes incredibly misaligned? How do we integrate across modes? And again, we've done a lot of work here in this space in this cross-modal integration space, but we still, again, a little bit of a persistent gap between moving that integration into decision, into reducing that decision latency, or thinking about how we can collapse the time from finding the indicators, from doing all of the modeling and the fusion that we need to do to begin to get a coherent picture on human environment interactions, and then moving that into insight. So again, the idea is that we try to think about what out of land system science and how can we go from that reactive to that anticipatory, with the ultimate goal of thinking about earlier warning, right? So one of the projects that I wanted to contextualize this in is this project that I've been leading since been working on since June of last year. And this was a call by DARPA, the Defense Advanced Research Project Agency, focused on agriculture in the Biological Technologies Office. And I got really excited about this opportunity. And again, this is why I'm kind of contextualizing my whole talk around this, because what this program was asking for, and this is DARPA, this is Defense Advanced Research Projects Agency within the Department of War. And it's a funding agency that, as a land system scientist and as a geographer, quite frankly, I never thought I was going to be working within or with, right? But when they put out this call for essentially, they were looking for how can we make agriculture more, how can we think about agriculture as a system whereby we can anticipate threats and we can create early warning systems to anticipate agricultural threats that may be crossing that are global, that may be impacting US soil, but not only US soil. We're working kind of on a global system. And that got me really excited. I've been working with a team of scientists from across 5 different institutions, 2 private sector companies, and a national lab to address under the umbrella of what actually became a funded project called AgScent, the Agricultural Security Early Notification and Threat Network, where we literally took the whole project is predicated on land system science, environmental intelligence, and geospatial intelligence, with the goal of taking the disparate data sources that we tend to bring into agriculture in the way that we analyze agricultural threats into a much more integrated approach. So basically, we're working on this tomorrow here. We're almost done with the project now, but we're really thinking about how can we transform agriculture from a reactive sector that is exposed to all of these threats, right? Globally, if you think about it, the interconnected and teleconnected nature of agriculture into a more anticipatory, coordinated layer of national biosecurity. So this is a slide from a pitch, and this was a oral pitch. So we've been doing this work. Like I said, we were one of 7 teams of over 520 teams that competed for this, that was awarded. So this was a very competitive award. And we've been spending the last 6 or 7 months working on how do we build this anticipatory shell of a proactive agricultural early warning system. And one of the threats that we've been working a lot around is the New World screwworm, which you've probably begun seeing a lot of media coverage on, which is kind of why I'm bringing it up here. And typically, it's something that we had eradicated in the 60s in the United States. And now we are basically back through a failure of, well, I mean, still to be determined what the failure is, but we're kind of coming back to a threat that is truly a concern for our American agriculture and North American agriculture, I should say. But we are still trying to understand, okay, what is it? What signals are there that we could be detecting, that we could be operationalizing from an early warning perspective, to prevent such a threat from entering U.S. soil? And again, the screwworm has already entered, so it kind of underscores why we need this kind of data. And this kind of anticipatory early warning thinking and environmental intelligence thinking. And this is just an example that we had used way back when we pitched this project way back as in December of last year, that shows through open source data, so open source intelligence, just data from this one of our private partners called Searist, on literally using social media to try to begin detecting where we might have conversations, and we might have people starting to think about or talk about the New World screwworm. Again, the idea of coming at arriving at early warning through a variety, that multimodal fusion, multiple data streams. So with this project of essentially trying to establish a global agricultural surveillance and early warning system, we've really come across 3 major sort of and DARPA calls them DARPA hard problems. They're really difficult scientific problems that are not necessarily solvable through even any of the current advances we have in software and even AI. And those stand to be in the 3 categories. How do we detect signals, or how do we create observational components for threats that move, that propagate across different scales and very different pathways? And how do we know when a signal, the meaning of a signal changes and viability changes for a threat, for example, as it moves through a system? And then how do we have confidence that these raw observations that we may be bringing into kind of a combined system actually are meaningful and they are attributable to a realistic cause, and they can inform the timely decisions. So we call this observation to action pipeline. So these are all really hard problems, and this is what we're grappling with right now. But for this specific project and this kind of specific early warning for agriculture that we've been thinking about here with this DARPA project, we've thought about the fact that these agricultural threats travel through multiple pathways, and we can use remote sensing and a variety of other sensing tools at various choke points or at various points in the way that these threats travel, but they do travel by atmospheric means. They travel via trade and logistics. They travel via biological vectors, via movement of humans and equipment, but importantly, specifically for this audience, via environmental corridors. And again, we stand as land system scientists to contribute a lot to this kind of broad thinking that even the Department of War is now really coming to realize is critically important for our economic viability, is how do we leverage what we do know from an environmental perspective to create a system that begins to alert us to potential threats. And so this is, again, kind of a contextualization of how we've designed this project to think around the idea of these interacting pathways, multiple choke points as threats or as pathogens or pests or viruses may travel via these many lines of communication, right? Whether it's trade logistics, atmospheric, environmental, and so on. And the idea that we want to begin to understand and to give that decision advantage to where if we isolate a threat, for example, as you can see here in my bottom right-hand side, that may be entering through a port, right, and maybe headed for a specific destination, we could potentially have the intelligence to isolate that threat before it moves through the system. So again, that's the strength of this set of thinking, and those of us that are in LSS, is that we have a huge advantage in understanding these environmental corridors, the way that threats and pathogens may move through detection, through socioeconomic signals, through in situ measurements, and through multi-scalar remote sensing and fusion across sensors, scales, and types, to where we can begin to think about what can we contribute that are decision grade products to kind of close that gap, to close the loop between signal and decision. So to take observations and turn them into decisions or that allow us to orient and to reduce that decision latency and to start thinking about, okay, where about attribution. And that attribution piece is another really big piece of thinking about agriculture as a globally connected system that we have completely realistically underestimated and understudied in this way, in the sense of really thinking about operationalizing a system that gives us the ability to act before a threat manifests itself. So this is accent, like I said, the idea that we're operationalizing land systems observations into a planetary scale early warning for agriculture and biological threats. And that's kind of what I wanted to leave you guys with. So again, going through and thinking about how we take these observations at a planetary scale and turn them into early warning for agriculture and biological threats. And this isn't just a small one-time, one-off project. It is a much larger program that DARPA and the Department of War are looking to create here. So you'll be seeing a lot more coming out in terms of even opportunities to engage on this in the near future. So I'm going to skip over some of these things because I went a little bit long. We started a little bit late, and leave you with, again, knowing that like I was trying to establish, there's a lot that this community can bring to operationalizing environmental intelligence for a variety of different uses, not only for agricultural decision making and early warning. And so I want to pitch this to everybody who's here with us today, and also my co-presenters here, to think through some of the things that we've really, as land system scientists, this isn't new. We've thought about these a lot, especially this number one. What turns an actual observation into a signal that could be used for decision-making purposes? And how do we decide on that threshold? As we know, there's been work in resilience and thinking about thresholds and tipping points for decades now. It's a similar line of thinking, but in this case, there's an actual demand now for operationalizing that kind of data into decision making signals. Then the other question I want to leave us with is where is decision latency actually lost? Is it in how we sense? Is it in where we do the sensing? Is it in how we integrate, or is it in how we are able to prioritize and create essentially uncertainty bounds around what we can say we should be acting on? So is that a trust issue? Is that on our ability to communicate that with the appropriate uncertainty estimations to actually turn that into decision-making tools? And then what it would take for land system science outputs to actually be trusted in an operational security context. And again, the other thing that I, as a scientist in this space, have been slowly moving towards is this national security context, really thinking about how we can bring environmental science into a national security context, but really, what does it take for these outputs to become trusted in that sense? And then lastly, this is a little bit of a difficult one. I don't think we're going to get to it today, but as land system science begins to move out of necessity, perhaps I would say, towards a more anticipatory security relevant use cases, what are we actually obligated from an ethical standpoint to weigh in from what we do? So with that, I will turn it over to my other presenters, and we will all try to stick to about 15 minutes so that we can have a little bit of time for questions. And I will turn it over to Prakash.
Perfect.
And if you have questions, I forgot to say, if you have questions at any point, I would love to start a conversation via chat. So you can put your questions in the chat, and maybe we can begin to talk that way. And I see quite a few people have joined, so we are excited to continue this, and happy to start the chat conversation. Thank you so much.
Very good. Good morning. Good morning, everyone. Thank you, Dr. Prakope, to setting the context. It made my work easier. Thank you for having me on the panel to celebrate the week of land system science. We all have become very good at collecting data about the planet, but the harder part is convincing the planet to wait while we analyze it. And at the land system science has given us those remarkable capabilities to observe, to understand environmental change. And the next challenge, what we are facing now, is transforming that knowledge into that actionable intelligence. So today, we can combine a lot of information from satellite to sensors, like socioeconomic information as well, to detect what kind of risk we are facing, and then how we can monitor those, how we can solve those. So as an agriculture climatologist, I see tremendous opportunity to move beyond those environmental chains and limits towards before we face those risks. So by integrating those data models and AI. For us, AI is not artificial intelligence. For us, AI is agricultural intelligence. So that's how today I will talk more on agricultural intelligence systems, where we we have more informed decisions for food security or climate resilient world for food production systems. So today I will walk you through some of the research we are doing at Mississippi State on land system science, which is evolving day by day, from an explanatory discipline into a decision support system or framework where we help societies, especially growers, become more resilient in this uncertain world. So I will walk you through a couple of the research case studies what we're doing on here at Mississippi State. So what we do here, we collect a lot of geospatial natural resource management and we combine it with a lot of tools, which are climate tools, a model tool. We combine this approach as a called SOAP approach, simulations and on-farm participatory research. We have sensors at the field, we have models in the lab, we calibrate those models, we run those models to develop a lot of scenario. That's how we work in our lab at Mississippi Agroclimatology Co-Laboratory. So I will walk you through a couple of case studies. So let's start with the model, what we do for modeling crop phenology. What we do, we collect a lot of climate data from different scale, from regional scale to local scale. We downscale those data and we collect a lot of field data from the fields, from different row crops to horticulture crops, and then we convert that data into a module collecting a lot of global soil data, and then we simulate. So what is anticipated outcome we can see from that? So when we talk to grower, they need real-time information for the state of Mississippi. Oh, what will be the flowering time for the crop? Why? Because they need to irrigate, for example, corn during silking time. They need to control this for disease management. They need to work on water management. They need these kind of crop phenology, means crop growth responses. That's how we do for most of the crops in the state and in the region as well. That helps in understanding how crop is responding to a lot of weather and soil parameters. This is one area we work on, and we anticipate to work more on the regional case studies as well. Another area we mostly work on how we can advance irrigation scheduling. So we all know the energy budget system from the land system, where we need to understand how much moisture is coming out from the earth's surface, right? Which is evapotranspiration. So from a lot of the models, we collect a lot of data for daily evapotranspiration, and we generate reference evapotranspiration to design irrigation scheduling. So at the farmer scale, farmer can go to each of the county, they can decide what they need to do based on irrigation scheduling. So we design a lot of crop coefficients for irrigation scheduling tool. Farmers can select the date and the area, region of interest, and they can design. So what I'm trying to convey here, for from the land system information, we translate into decision system, how they can use those information for daily purpose or maybe in terms of the field season. So this is the second area we are working on. In the third area, we are also working on in the Delta region of Mississippi. We all know this is highly intensified agriculture region. We try to understand how water management is connected with food production. Especially for Delta region, they use a lot of water from the groundwater. So we need to understand how both are connected. So we are connecting demand and supply side of water. So groundwater studies from remote sensing, and then supply side from different models as well. Demand side is evapotranspiration, where we have a lot of data from remote sensing to the models. We connect and we balance those demand supply side to develop a decision support for the farmers, where they can combine their field planning for total water requirement. They can monitor their well water withdrawal. They can also monitor how they are extracting those groundwater for decision making in the field. So that's how we're trying to understand how food water is correlated and how we can make a decision based on those. And this is tightly linked with the energy budgeting of the water, which is, we can say, food water energy nexus as well. The another area we are trying to connect, which is long-term climate mitigation plan. So in the Delta region, we have a lot of rice farm. We have a lot of sensors in the field for collecting methane data from the field. The methane is, coming out from the rice or paddy field, where we have a lot of water flooded condition. We compare with alternate weighting and drawing as a alternate practice as well as conventional practice to understand how the soil microbiology helps in understanding those methane flux from the rice field. So we are connecting molecular level, which is microbial level, to the satellite level to understand how we are connecting microbial modeling to the methane based modeling from the field to satellite scale. So we are connecting those land system from scale of microbe to scale of satellite to understand how we can plan on climate mitigation plan. So one of the unique approach for rice fields is alternate wetting and drying rather than conventional flooding. And in that domain, the carbon plays significant role. So we try to also understand the soil spectral intelligence for climate mitigation plan. We all know there are a lot of multispectral data. We try to generate hyperspectral data from multispectral data, which means using UPDM, Universal Pattern Decomposition method, we are generating hyperspectral data set where we don't have data set available right now. I'm sure next 10 to 15 years, we will have a lot of hyperspectral data to understand. Right now, we are developing limited database for from multi to hyper, and we are generating a lot of index-based SOC maps, soil organic carbon map, how it will look like. So we are connecting with geospatial embeddings of Google Earth Alpha model, and we are also connecting with a lot of simulation models to understand what is the present status, what will be the future condition for the soil carbon, to understand those of carbon sequestration program or maybe carbon credit program. If you know about that, mostly we try to understand the carbon density or carbon uh, availability in the soil to understand the carbon credit program for different practices. So that's how we try to understand at geospatial scale in the region in the mid south. That is one area. Another area we are also working on the dashboard where we can see the land use practices which are involving a lot of practices based on forestry and agriculture, which accounts a lot of carbon accounting for capture as well as emissions. So we try to collect a lot of data from different sources, from satellite to field, and we collect those biomass estimation, and then we also compile emission measurements. And then on all those topographical variables and soil variables, you can see the crop type, and we identify the hot and cold spot of carbon sequestration. So it means if you're a planner, if you are a policymaker, you will look for those hot spot and cold spot area for long-term sustainability planning. And that's how this kind of dashboard will help in decision making from county scale to state as well as national scale. And then Dr. Prakopi was talking about National Security of Environmental Resilience Plan, and these kind of information will help into understanding Mid-South contribution to the national resilience as well. So I will just summarize what we are doing. I just gave a couple of examples what we are doing, but whatever we are doing for environmental intelligence in agriculture with the goal of 5P. The first P is how we can enhance productivity. Ultimately, goal is to enhance farmers productivity, so they look for working with biological sciences, forestry, plant and soil sciences. We work together on enhancing input use efficiency for fertilizer, for water. So first goal of the grower is to enhance the productivity, and that's how for all agriculture intelligence we look for. Number one priority is productivity. Number two is how we can protect. Second P means we have a lot of stress from biotic, which was talking, Dr. Prikopa was talking about biotic stress, but we have a lot of abiotic stress, which is drought and flood, and we need to account those abiotic and biotic stress. These kind of agricultural intelligence lead us to understand those kind of stress and how we can manage those stress, so how we can protect the system. So number three is how we can predict. We know the current condition through monitoring, and then we simulate for future conditions. We try to understand what will be the impact on certain practices or impact of certain practices on the system. So we try to predict those system based on current and future condition as well. So number four is prescribe. When you go to doctor gives you medication, let's say to morning to evening. Same to the grower, we talk to them how to irrigate, how to fertilize, when to fertilize. So these kind of prescription, we develop a lot of scenarios using a lot of models, AIs, as well as satellite data. Last one is very important, which is missing link in most of the research practice. Whenever we develop technology, the practice is a missing link, means adoption, scaling up, market connect. So we work with extension team, economics team to translate those research into actionable tools, farmers field days, and then they are the real decision maker, right? So they, whatever land system information we are creating, we are developing, these all go to decision system. So practice is a connecting link which we are working day and night, but still we need to work more on the practice. So this is overall 5P of agricultural intelligence in the land system science we're working on. I'll stop here, and then at the end we will have a lot of questions. So this is a map of state of Mississippi. It looks like face. So without collaboration, you are just another person with an opinion. So we work in a lot of collaboration with people like Dr. Prokope and other. We try to investigate the problem. We try to find the solution for this problem. I will stop it here. Thank you.
Thank you so much, Prakash. And you are one of the most collaborative people I know. So, and you really do care about operationalizing and decision-making products. So it's really, thank you so much for your contribution. That was a great overview.
Thank
Debrat, I'll let you go next so that we can mix it up a little bit. And then we'll finish up with, please think about any questions you may have from what you're seeing, and you can start putting questions in the chat. Thank you so much.
Definitely. Thank you. I hope you can see my screen now. Can you hear me?
Yeah, yes, we can.
Yeah.
Yes.
Cool. Yeah. So hi, I'm Devrat Varsne. I'm at Oak Ridge National Lab, and I'll be giving like a high-level overview of like remote sensing and how we can generally use it for simulation and for forecasting purposes, so that we can get a sense of what the future looks like, and have like that sort of, as Narcissa said, like reduce the decision latency. We can get a sense of what uh, future would multiple scenarios of the future would look like, so that we can prepare ourselves and be more resilient for the future. um, so yeah, remote sensing is this like amazing field. I've been working on this in like 5 to 6 years now, but I'm still like amazed by it, by the different types of sensors that we use, from multispectral, hyperspectral to like lidar and radar, where you can like sense different characteristics of the earth at multiple resolutions, multiple scales. And it has many downstream applications, leading from like flood mapping to wildfire detection, and even like ship vessel detection, to agricultural crop yield prediction. So in this overall sense, we can also like fuse different sensors with weather monitoring sensors, which like map atmosphere, humidity, moisture levels of the earth. And you can like have these multi-scale or multi-fused models that can synthesize of what the future might look like. So remote sensing can like bring about a lot of applications, especially for security purposes and resilience planning. Like one of the very useful sensors is like this SAR sensor, where you can uh, like have an all-weather capability across different weathers or cloud-free atmosphere. You can sense it through nighttime also, and you can detect like each small ship that can be like an illegal smuggling, or a small fishery boat that you want to get a hang of. Apart from that, you can also get a sense of different soil moisture levels, and the different types of land cover that exist across the earth. And so this is a really nice sensor to like build like robust pipelines of for your region. Also, another application is like wildfire monitoring using hyperspectral data, where you can monitor not just what the burns have happened in the past, but if you build like good AI models, you can deploy them so that you can predict what the next potential area of wildfire might be. And in this regard, there have been like recently constellations by Google called like Firesat, where you have models deployed on the edge on the satellite sensor itself, where you're not just like transmitting raw imageries back to the earth, but you're actually transmitting decision intelligence to the end user, where you can like detect certain levels of early signals of like cool fires, where in which regions they might come up, rather than like waiting for an actual wildfire to occur and then sending firefighters to fight post the event. So yeah, in this scenario of like having multiple sensors, multiple capabilities, we can like fuse them together to model what the Earth might transform to in the future. So it can be both in terms of like environmental intelligence, like how these biophysical parameters like affecting each other, or it can be in terms of like security intelligence as well, to have a more resilient future for both humans and for the environment. Uh, Another important aspect of this is like how humans are like collaboratively uh, engaging with the environment, and it's like a feedback loop where human activities define how the environment is changing over the next 5 to 10 years, and the changing environment then in turn affects our day-to-day activities and our lifestyle cases as well. So we want to study of what the past trend has been like, given this massive amount of satellite sensors, and we want to start leveraging them, what the future scenario for the earth would be. We also want to add capabilities of simulations, like if, for example, there is, say, extreme snowfall in Southeast USA, uh, what would that mean for our cropping patterns? What would that mean for our agricultural practices? So we can like think about generating these digital twins for specific scenarios, or simulating specific scenarios, so that like we are well prepared of what the future would be. And in all of this system, land cover or land surface becomes like one of the key aspects, because uh, that is where our human ecosystem is like directly defined, or human activities are directly defined, in terms of like urban development, regions which are developed, or um, patches of land where we are practicing agriculture or farming. And the more urban dense an area is, it could also lead to higher temperatures, which like affect climate cycles eventually. um, the more developed a region is, it would have like lesser groundwater infiltration. Rainfall would be percolating lesser into the ground, and that affects like the water cycle as well. So land change becomes like this key aspect of this whole environmental cycle, water cycle, and so forth. And so studying land is not easy. It can be like driven by multiple different types of data sets, historical images, satellite imagery, and elevation, soil maps, and so forth. But like processing them at together, it's like a huge task, and especially if we want to model for the whole country, seeing all the geospatial patterns across a country as big as America, it's a big challenge. So in one of our works, we've been trying to use this problem as like to define how land cover would change over time, and we want to use this to see how this would affect like flood models eventually. Like I said, like uh, the high imperviousness levels across like urban lands affects how much water gets infiltrated into the ground, and that affects like water cycles. So we want to like simulate uh, land cover generations for the future, so that they have like an impact for multiple different applications. And our approach that we have taken is like using these diffusion models, gen AI based diffusion models, where we want to simulate the next few years. So as the latest models, you can like prompt them with text or with like individual image frames to generate the next frame. We want to use the same capability and like synthesize of what say my future looks like 10 years down the line. And so we've been like building these models for the entire US. We've like leveraged like a national land cover database where you can see the whole country with different classes, land cover LULC classes, and each like 30 meter cross 30 meter pixel is defined into a vegetation or an urban developed land or a farm, and you have the same area has been defined into different levels of imperviousness, and we've been like training these models with these diffusion architectures where you can have multiple conditions on the model. It can be like driven by multiple different modalities. One of them could be like LULC, imperviousness, or the elevation, proximity to road network, so that you know how cities are like evolving over time, like how their morphology will change, in 5 years, in 10 years, in 20 years. So that really helps us be prepared of be prepared of what the future would be. So just an example is, so these models can like take in historical information, like imperviousness and LULC class labels, and if you have a reference ground truth, they can like synthesize from 10 years down the line multiple different possibilities. So it's not just like a single scenario that they are generating. It can be like uh, because land cover itself, it's very like driven by human activities. There's no like single output what human future or the earth's future would be. It can have like multiple different scenarios. So that's one of the advantages of using a diffusion model, that you can have multiple scenarios of the future, and you can also condition them or prompt them with like specific information as compared to these older GAN based networks. And we also want to start thinking about, even if we are building these AI models, how well they work across scales. So our decision intelligence is being happening at like a coarser scales or at finer scales, and because each scale would mean have different relevance for different impacts. Um, if you're looking at like smaller scale changes, like from building level or city level, or are you looking at like wider changes across entire cities, or southeast regions and so on. So yeah, we had these models trying to forecast imperviousness, where we compare it with like a null model, and it's like gives like a good amount of accuracy in terms of prediction errors. And we also evaluated for multiple like areas of interests across US. So ranging from highly dense regions like Vegas, Miami, or New York, to very rural areas like maybe Beaumont, um, so that we have this spatial diversity of all the regions across US. And again, so these AI models are very expensive, like to train, and might take like a few weeks to train like a good, robust model. But it's important to have a sense of what it means compared to traditional rule-based models, which are more specific on like the spatial patterns, and so they only are focused on regional areas and maybe not as diverse as a data-driven AI model, because it's like consuming so many chunks of diverse data sets. Uh, so yeah, and we've also been like exploring the use of these models for specific changes. So like I mentioned before, if you want to simulate a specific scenario of 10 years down the line, if what change might look like. So these diffusion models bring a capability that hasn't been there in GANs as such, where you can like prompt them as per your convenience. You can prompt them to your requirements. And so, for example, if you have like images from the historical timestamps from, let's say, 2004 to 2014, where you can see the development happening, and it could be like for different applications, like even for agriculture, you can like monitor how the crop types have been evolving. So yeah, if you have a sense of how development has been growing, you can get a sense of what future would look like if I say it's just growing at, like, let's say 10% of the rate of 2014. What would 2024 look like? And I can also like monitor or control my synthesis levels of what change would mean if I just grow at like 25% of the rate or 50% of the rate and like 75% of the rate of just 2014. And the advantage is like it's just so much data, diverse data, that it can able to
Right.
simulate at the right spot where development might occur. So it's not just like random hallucination that the model is doing. It's like pretty accurate, and like this is a ground truth that we are just comparing with. It's more or less pretty accurate in terms of like spatiotemporal allocation of
Mhm.
change. And so this helps us being more preemptive or being more resilient, rather than using these AI models uh, uh, as like these reactive models, or you have this historical data and you just predict a map out of it. But this really helps us in being resilient for the future, and having urban policies that can define of where where to start developing, where in which areas would you rather have like farms growing, or which areas would you have water bodies and so forth. um,
Thank- Devrat,
uh-huh.
sorry. Oh, you're
So, well,
summarizing. Okay.
yeah, I'm
Yeah,
sorry if I'm
okay.
going beyond.
Sounds good.
Yeah.
Thank you so much.
So yeah, overall we've been just try to forecast land cover changes with these models which have leverage data-driven a lot of data-driven capabilities, and multimodal aspects with like elevation, zoning, and so forth. We can also condition these models with like urban policies. So imagine like if you have latest urban policies that you can describe in a text form, and you can feed that text into these conditioning architecture so that your future synthesis is more driven by human knowledge and not just like imagery data. And I just like to leave with, as we are going into the future, there is a lot of emphasis on AI and data centers and so forth. So we really need to be secure about how we are going to plan our land structure and land activities, because this will directly impact the environment and ourselves in eventually. And security is not just about like from outside threats or international threats or foreign threats. Security can also be from internal natural hazards, calamities which are happening inside, and like biological or agricultural pests as well. And we need to have safeguards to be prepared for the future. So yeah, thanks.
Thank you so much. Really appreciate that. Any questions for Devrat? Please put them in the chat. We are running a little behind for our discussion at the end, but hopefully we'll have a few minutes. But please put questions in the chat in the meantime. And now I'll turn it over to our last speaker, Nafiz Rahman, who will talk about some soil carbon monitoring research in support of early decision making.
Yeah, so can you hear me and see my screen?
Yep. So,
Okay. So I'm going to present a experimental case where we try to monitor soil organic carbon on Guatemala, and we are going to connect it with the decision support system, how this experiment can help us make some decisions on land forms, land restoration, or land degradation. So this is a NSF funded project. So why do we need to monitor soil organic carbon? So one of the important factor is that it is the largest terrestrial carbon pool. It stores more than twice what the atmosphere has in terms of carbon. And even a small fraction of change can have a large impact on climate and fertility consequences. And it is one of the major indicator of land health, according to United Nations Sustainable Development Goal 15.3.1, where there are three sub-indicators, which are land productivity, land cover change, and also the soil organic carbon. And it is hard to monitor over time. We don't have a lot of in situ data, globally speaking, and we only have soil grids, but soil grids data is not well distributed across the globe, as you may know. So it is actually difficult to detect soil organic carbon from remote sensing and any kind of other methods. So there are two major advantages for this experiment. One is that we are using multi-scale sensing.